Yes. Ilya, start recording if you can.
Έχω πατήσει το recording. Νομίζω ότι... Okay. Leonardo?
Okay. So, hi to everybody. So thanks, Yanis, for this nice invitation. Thanks, Elias, for organization. So I guess that we already met, maybe in physical presence 1 year ago or 2 years ago. So I would have liked to be there with you, of course, but we cannot. So hopefully next year. So I guess you can see my screen. For any doubt, any kind of technical issue, please interrupt me and tell me whether the screen is not it's not there. So please interrupt me, and I can try to fix everything. Okay. So
Leonardo, put full screen.
Yeah. Now. Okay, you should see my full screen. Okay.
Okay, I will leave you now.
Oh, okay, then I guess I will be also using R quite quickly. Let's see with the time, but let's see. Okay, guys. So today I'm going to have a very quick introduction to some Bayesian models in Stan. So I saw that you already had a quick introduction to Stan. I'm going to review something. I will be quite let's say fast in some slides because of course in 2 hours we have to be fast. So Stanislav Ulam is the person thanks to which there is the name Stan. He's one of the person involved in the Manhattan Project, in the H-bomb in Los Alamos in the 50s of the 20th century. So the name Stan is due for that for this reason, for this very brilliant person working with Fritz Metropolis and other scientists, also with John von Neumann in the Los Alamos experiments. So a quick summary of Stan. So what is Stan? You already know that Stan is a probabilistic programming language in which you have to declare data, define the log posterior. You can have inferential conclusion. You can get inferential conclusion by using, for instance, the MCMC techniques like the Hamiltonian Monte Carlo, which is an extension of the usual MCMC techniques, or you can also use variational bias. I'm not going to say anything about variational bias because variational bias would be another very long course. Of course, I'm shrinking much material in these 2 hours, so we will be speaking about the approach of Hamiltonian Monte Carlo, then the extension of Hamiltonian Monte Carlo for full bias. The nice stuff of Stan is that Stan is a very big ecosystem with many libraries, interfaces. Stan can be used also with Python, with Stata, with Julia. So many interfaces, much documentations. There is also an online community and the Stan forum for which you can write there for any kind of problem. So it is very well maintained. I personally know some of the guys working there, and I can tell you they are incredibly effective also in answering many questions. So why using Stan? Because you can fit rich Bayesian statistical models. It is somehow close to the big data philosophy, in which big data may refer both to the number of units, but also to the number of covariates that you have for your regression models, for instance. Stan is very efficient because it is using an extension of the MCMC, so the Hamiltonian Monte Carlo with the NUTS algorithm, to be specific. I guess that you already had a quite introduction of this. I can give you some material more if you want, some papers about this. Hamiltonian Monte Carlo is is much difficult to be understood deeply. One of the guys working there once honestly told me there is only one guy inside Stan that really knows all the details of Hamiltonian Monte Carlo within Stan. So try to think that Hamiltonian Monte Carlo is very difficult. So the nice thing, and we are going to see something today, is also the interaction with some other R packages designed to explore the Stan outputs, such as, for instance, the bias plot package and also the loop package. Many people are using Stan in biological and physical science, social science, but many more. Sports analytics people, public health, publishing, finance. And the nice stuff of Stan, it is the richness, the interfaces and the tools. Also, for instance, with the package RStanArm, the package RStanArm is a sort of shortcut that allows you to fit some very, let's say, plain models, such as the generalized linear models, but also hierarchical models, directly with one line of code. Of course, you have to be in some sense familiar with the idea already with generalized linear models and hierarchical models. And in some sense, you lose some flexibility because whenever you just use one line of code to launch a model, of course, you are assuming many stuff. But of course, with RStanArm, you can, for instance, fit generalized linear models in a Bayesian framework just by launching one line of code. So why Stan is so effective and why Stan is so much used? Because basically Stan is enjoying an MCMC implementation that works quite robustly. We know that Gibbs sampling and random walk metropolis can be quite inefficient and hard to diagnose. So for instance, for what concerns the so-called random walk behavior of the metropolis hustings. So Stan is very well suited for exploring complicated high-dimensional spaces, in some sense to explore what is called the typical set. The typical set is the real space, is the real domain of the posterior distribution worth to be investigated. So the typical set is defined as really the, let's say, the interval, the domain space for which it is worth to be, it is worth to explore the posterior distribution. In some sense, Stan users can use Stan outputs and Stan even with no knowledge about the Hamilton and Monte Carlo, because it is sufficient to know the basics from MCMC. So if you already know something about MCMC, this is basically enough. So of course, if you want to become quite expert and quite even more, let's say, expert about the Stan, about how Stan works, okay, then I guess you can take some hours to spend some hours in improving and in learning how Hamilton and Monte Carlo works. So in these 2 hours, we will see how basically to build Bayesian models, but you already know this. And in some sense, we will understand that specifying a Bayesian models, especially in the Stan logic, basically is a joint model of the observable and of the unobservable. So the philosophy of Stan, the philosophy behind the Stan is to think generatively. So the model is expressed as a joint probability distribution of the data, the y, the observed, and the unobserved variable, the parameter, which may decompose as follows. So the joint distribution of the observed and the unobserved can be seen as the product between the likelihood and the prior for your data. So you already know from Bayesian theory that the posterior of interest is then proportional to this product here. So it is proportional to the joint distribution. Proportional because here I'm not putting directly the proportionality constant at the denominator of the posterior distribution. So the nice approach of Stan is thinking generatively. So we can think at a sort of joint model for the observed and the unobserved. So in some sense, we can also make a sort of mind exercise and see that whenever whenever you think at a joint model for the observed and the unobserved, you can see it as the product between the likelihood times the prior, but also as the product between the posterior times the marginal likelihood. And the marginal likelihood is exactly the denominator of the Bayes theorem, the denominator which is somehow very, very difficult to be explored, because that integral that arises in the denominator is usually analytically untractable. So we will be understanding also that Stan works in a logic of weakly informative priors. So why weakly informative priors? Weakly informative priors became very, very popular with the Gell-Mann approach because, of course, in Bayesian analysis, you are encouraged to put your information into your parameter according to your prior distribution. Whenever you have some information, you can directly specify your information into your prior distribution. But even when you do not have much information, in some sense, you are not encouraged to use very vague and diffuse priors, which can lead somehow and sometimes also to not proper posteriors. So sometimes, and Stan uses this logic, it is quite suggested to use what is referred as weakly informative priors. Weakly informative priors are usually referred as those priors that also, in some sense, regularize the inferences. Because, for instance, there are many cases also in logistic regression in which the use of non-informative priors can be somehow, can have some very poor consequences in terms of inferential conclusions. So let's see that the logic of Stan is quite different from the logic of bugs, from JAX, to use very diffuse priors with very, very high standard deviation, but in some sense to restrict the domain. In some sense, In STAN, we are asked to restrict the domain of credibility for our parameter. So, as I told you, if we disallow improper priors, then Bayesian model is really generative. In particular, we have a simple way to simulate from our marginal likelihood. If you think we need to make a sort of two-step process in which we generate before a theta star from my prior distribution, and then I sample a y star from my likelihood condition on the sample of theta that I already generated. This is basically equivalent to generate directly from my marginal likelihood. And this is basically what is called a generative model. So my prior values here should be, in some sense, realistic values. And you should already understand that the more realistic is the prior, and the more realistic will be also the observable and replicated values that I'm sampling from my data mechanism process. So only by using, let's say, some realistic priors, so not so diffuse priors, basically you can have a generative model. And this is the logic of STAN. STAN works in logarithmic terms for convenience, for mathematical convenience. So the logarithm of the posterior, of course, can be written as the logarithm of the prior plus the logarithms of the likelihood plus a constant. Of course, the products become sums of log. So if the likelihood is defined as the multiplication of the single contribute to the likelihood, then of course, the logarithm of the likelihood is defined as the sum of the single contribute of the likelihood. So I guess that you already had a glimpse on how STAN works. There is a block strategy. So STAN programs are organized into blocks. There is a data block in which you declare data types, size, constraints, and this is particularly new. This is not something which is happening, for instance, in JAX or in WinBags, where you have no need to declare your data. Instead, in STAN, you need to declare your data before, the constraints, the sizes. Then there is a parameters block in which you declare parameters types, size, and constraints. So for instance, you can declare the standard deviation for your normal distribution. And of course, the standard deviation needs to be constrained between 0 and plus infinity. So of course, you have to use that constraint when you are using parameters. So in some sense, you have to translate the physical nature of your parameters. There is then a transform parameters block. Here you can declare those parameters transformed from the original ones. We will see examples of this in this lab. There is then the model block containing all the statements defining the posterior density in the log scale, and then there is the block of generated quantities, which is something completely revolutionary, because in this block you can define all the replications, both in sample replications from your model or out of sample replication, meaning some predictions, for instance. And this block is quite relevant, because with this block you can, for instance, generate hypothetical replication from your model and check whether your model is consistent with the data that you observed and that you used to fit the model. So just to be very, very quick, just summarize the blocks strategy. So of course, this is a very simple, rough linear model. So you have the data block, the parameters block. Here, as you can see, when I'm when I want to define, for instance, the standard deviation, I have to put a constraint, so real with lower equals 0 within these symbols here. I don't know the English term. I guess hyphens for this. I never remember the name for this symbol in English. Sorry. There is then the model block. There is the model block in which I can assume, for instance, some possible priors for my parameters, and then, of course, also the likelihood for the model. If I'm not defining any kind of prior, in automatic, STAN is considering that I'm using a uniform prior. Why? Because, of course, when I'm using basically a uniform prior, this basically means that my prior distribution is proportional to 1 over all the domain space. So this means basically that in log scale, this is 0. So I'm adding 0 contributes in terms of log scale. So nothing is added to the log probability. Remember that STAN works in log probability. So the posterior is defined as the log posterior. So basically assuming a very diffuse priors, basically means that I'm not adding any kind of contribute in the log posterior. In the generated quantities, as I told you before, you can define hypothetical replications. Hypothetical replication from the model, as we will be seeing, this is quite relevant for understanding how the model is able to generate values which are, let's say, close to the data that I observed. So yrep is usually the notation that is used. I have to generate a yrep vector with, this is a vector of dimension n, which is the data dimension. And for each n, I'm basically generating a value which is let's say the copy of the real value that I observed. So this will be relevant for the so-called model checking approach, to check whether my model is able to provide replications of the data as close as possible to the data that I observed. If the model is not able to generate, let's say, close replications to the data that I observed, maybe there is some problems. Maybe my model is not feeding my data in an adequate way, in a good way. So maybe I have to do something, and we will see how to work in this scenario. So the complete stand model, data, parameters, model blocks, of course, here there could be also a transform parameters block, but these are basically the main ones. And then the generated quantities block, in which basically we simulate from the generative model. Here is just a very, very simple slide in which I provide something that you already know very well. So the function stan, the file, which is the name of the stan code. I always suggest you to write the stan code in a separate file. So please do not write your stan file directly in your R console into your R script, because this is somehow confusing. So please always, in my opinion, write your stan model in a separate file and call it with, of course, the suffix .stan. Let's start with a very rough example. This is usually adopted by the stan community to explain how stan somehow works, but also to explain some very initial but very, very useful stuff. So this is the 8 school example. This example studied the coaching effects from 8 schools. So each school had a different coaching effect, and we want to observe the result of the height test in the J school. In some sense, we want to check whether some school perform better or worse according to these coaching effects. Of course, the coaching effects are unobservable. So I have to assume, let's say, a theta parameter for each random effect, in some sense accounting for the fact that the random effect come from the population distribution of the random of the coaching effects. But of course, I will be needing to estimate these different coaching effects. So this is basically the plain model, the simple model, in which this is a hierarchical model in which for the ith student in the J school, I'm assuming a normal distribution with theta j and sigma square y. This is the individual variability, and theta j is sampled directly from a normal distribution. The data usually that the data that are provided usually are already aggregated by school. So usually in this data example, the data are already aggregated by school. So I have 8 different schools. I have directly the number of y, which is the average of the test in the different school, and associated to each school, I have also a measure of standard deviation. So basically, what I do is using the aggregated values for the schools, in which I have 8 schools, J, Yj are the test scores for each school. Of course, I'm defining here a sigma different for each school, and then the model block in which I'm defining a normal regression. So very, very simple model, theta and sigma. So I don't care a lot about this model because this is a very simple model, and I don't want to focus so much on this model. But let's go to analyze something, because in what follows, I want to give you some let's say, initial practical use of the bias plot package, which can be very, very effective to analyze the stan output. So we can feed the model with the stan command, but now let's see what we can do with the bias plot package. This is the first example of package which is related in a very efficient way to the stan ecosystem, because the package allows to display, for instance, posterior uncertainty intervals, univariate marginal posterior distribution, bivariate plots, trace plot, but also we will be seeing in a while posterior predictive plots. So for instance, the first step is to save the posterior. So once you fit the model with stan, you can save the posterior with the s.array command. So let's write s.array fit 8 schools, and then you have a bunch of functions, all starting with MC underscore intervals, areas, density, pairs, and trace, for which you can directly obtain some very useful plots about the posterior. So in this step, we are just analyzing the posterior distribution. In a while, we will see how to use this package and the functionality of this package, also to explore other aspects of the model, to check the model. So the intervals, basically here, this is a very, very simple but effective intervals for all the parameters. So basically here we can report the posterior uncertainty intervals at the 50 percentage level, at the 95 percentage level. So the solid line represents the 50 percentage posterior intervals, whereas the thinner line is representing the 95 probability posterior uncertainty intervals for all the parameters. With the MC areas, you can basically retrieve something even more sophisticated, because you are not just retrieving the intervals, but you are retrieving also the marginal posterior for the parameters, and you can also in some sense check for the skewness of your parameters. We can also find out the marginal posteriors in terms of the different density functions. You can do this also by analyzing, for instance, the marginal posterior separated for each chain, because of course, as you know, when you fit your stan model, you have to fix the number of the number of Markov chains used for the Markov chain algorithm. So for each chain, you can retrieve, in this case, also the different densities, and check, for instance, that in this case, the different densities are quite undistinguishable with respect to the different chains. And this is basically something that we expect. Or also, you can also produce some bivariate plots. So bivariate plots for instance, in this case, should be tau and mu. So you can also produce bivariate plots for 2 separate parameters. And of course, trace plot for the Markov chain. So here you get all the process of the Markov chain. And again, this is quite easy because it is sufficient to get MC underscore intervals, areas, and so on posterior. You can have many other arguments, basically some aesthetics arguments, of course, to deal with this aspect. But let's say that with this package, you can visualize in a very effective manner all the let's say, aspects from your posterior distribution, from your marginal posterior distribution. So our challenge with stan is basically write a simple and more complex model, analyze the posterior summary, and then criticize the model and eventually change and reparameterize the model. I'm putting here some further reading. So basically this lecture today is divided in parts. So this first part is a very, very quick and rough introduction. I'm putting some further readings. For instance, the Carpenter and Gellman and et al. Paper about stan published in the Journal of Statistical Software. And for those of you who are interested in the theory of Hamiltonian Monte Carlo, I can suggest you the paper from Michael Betancourt, a conceptual introduction to Hamiltonian Monte Carlo, which is very, very effective because it is quite, let's say, it is very, very, it has a lot of graphics, a lot of plots, so it's quite effective because it is guiding you in understanding the Hamiltonian Monte Carlo also by using many, many plots. I guess I put these papers in the further material folder that you find by downloading the folder of the lab from GitHub. Okay, now let's start and let's go towards one of the main topics of today, which is model checking, because I don't know if you're familiar with the model checking in Bayesian terms. I guess maybe you have already encountered. But once we have accomplished, let's say, the first two steps of Bayesian analysis, so constructing a probability model and then computing the posterior distribution of all estimates, in some sense, we should go towards a further step, which is not something less relevant, of course, because we should check the model. So this is a relatively easy step because we have to assess the fit of the model to the data. And in some sense, we have to check whether our choices in terms of the prior, in terms of the likelihood, were appropriate or not. Let's say that in Bayesian terms, we use the term model to encompass both the sampling distribution, the prior distribution, any hierarchical structure, and issues, for instance, related to the covariates, which are included in our regression model. So once we got the posterior distribution, our work is not done. Our work is, let's say, in the maybe at the 50%, because now we have to assess the goodness of the model. We have not to ask ourselves if our model is true or false, because this is, I mean, useless. As George Box said, all models are wrong, but some of them are useful, of course. And so how can we judge, in some sense, whether our assumptions that we made to build the model are appropriate or not? So basically, we can check a model by external validation using the model to make some prediction about hypothetical data, and then collecting those data and comparing to the predictions. So in Bayesian analysis, usually we use what is called the posterior predictive checks to check the joint posterior predictive distribution of future data given the data trend, future data, or eventually hypothetical replication from the same data that I used to fit the model. So the idea basically is the following. If the model fits well the data, the replicated data under the model should look very similar to the observed data. To put in another way, the observed data should look plausible under the posterior predictive distribution. So we should, in some sense, draw simulated values from the joint posterior predictive distribution of replicated data and compare this sample to the observed data. Let's say that any, let's say, difference existing between the simulation and the data indicate potential failings of the model. And if we notice that there are some failings in the model, we should ask ourselves, okay, should I go back? And maybe should I criticize the choice of the priors? Should I criticize the choice of the likelihood, and so on? So basically, you are checking your model as a whole. You are checking your model for everything. I mean, not only for the choice of the likelihood or not only for the choice of the priors. We define YREP, the replicated data that could have been observed. In the following, we will be distinguishing between YREP and Y tilde, because Y tilde is any future observable values or vector of observable quantities. So this is basically an auto-sample replication. So basically, this is a prediction ahead. Whereas YREP is specifically a replication just like Y. And this is what is typically said an in-sample replication. So this is a copy of my data. So let's suppose that I want to model the height of this class, the height of this virtual class. I use a linear model for this class. So basically here it should be 30 students. I don't know, 30 students. I use a linear regression for modeling the height of this class. And the only covariant I use is the weight. What does it mean this? What does it mean checking whether my, let's say my model is able to fit my data well in Bayesian terms? I should sample from my model, let's say 30,000, 300,000 potential replication of my data. So I basically sampling from my model 30,000 new heights for each of you. So basically what I have is a data matrix with dimension S, number of replication, and S rows and N columns. Each row is a replication of a vector of the class. So basically, I will have 30,000 replications for the height of the class. So I will have 30,000 vector of dimension n for the heights of this class. Of course, if my model is good, in some sense, the replicated vector for a class should be the more similar to the data that I observed. Because, for instance, if my replicated vector is saying that the women in this class are tall, let's say 2 meters, and maybe the model that I use is not, of course, suited enough to describe the data. So basically, by using this matrix of replicated observation, I should be checking whether my data is able or not my model is able or not to replicate the data that I observed. The techniques, the usage is about the posterior predictive distribution of Y-rep. So the posterior distribution of Y-rep is defined as the integral of the product between the likelihood for hypothetical replication times the posteriors. So basically, we measure the discrepancy between model and data, usually by defining some test quantities, which represent the aspects of the data that we wish to check. T is a scalar summary of parameters and data that is used to compare data to predictive simulation. For instance, I can use the mean of this replicated vector. If the mean of the replicated vectors for the height of the class is, let's say, 1 meter and 90, maybe the model is overestimating the mean of the class. Conversely, if the mean of the replicated vectors is 1 meter and 40, maybe the model is underestimating. If the mean of the class is something like 1 meter and 70, maybe the model is okay, it's somehow describing my data well. So let's say that in the 8th school example, how can we do model checking? So when I want to do model checking in this very, very simple example, and then we will have examples, more advanced examples for more models, basically we have to take into consideration many stuff. The example that we had is based on many assumptions. So we are assuming normality of the estimates given theta j and sigma j, where the sigma j are assumed known. We are assuming exchangeability of the prior distribution. I didn't go in depth with this, but basically we are assuming that in some sense, all the theta j are exchangeable. We are assuming a normality of the prior distribution of each theta j given the hyperparameters mu and tau. So in some sense, we are making many assumptions. And when we want to make some model checking, in some sense, we are possibly criticizing all the aspects of the models that we put to build the model and to fit the model. So in practice, how can we do model checking in Stan? Nothing so difficult, because all we will do is simply by approximate this integral by, let's say, a two-step simulation. What does it mean, two-step simulation? Two-step simulation, we need to discretize this integral. So for each bunch of the posterior distribution that we have, we will be sampling hypothetical replication condition on the values of the parameter that I obtain via the posterior distribution. So let's say that I have a capital S number of possible replications from my posterior distribution. How Stan works? How does Stan work? For each sample of the posterior distribution, for each theta S, S is small s to indicate the S replication. Basically, I can obtain a replication Y-rep, an hypothetical replication for my data. So basically, the logic of Stan is approximate the posterior predicted distribution, which is usually unknown and intractable, unless a few cases. So by approximate this process via a discrete process. So for each, let's say, step of the Hamiltonian, for each step of the Markov chain algorithm, I should then obtain a new data vector according to my likelihood given the values theta obtained from the posterior distribution. This is more difficult to say than to apply, because this is basically translated in what? In the generated quantities, it is sufficient to store a Y-rep vector. In this case, I'm using the notation real Y-rep J, for each J, Y-rep J is a normal with theta J and sigma J. So take into consideration and pay attention on this, that this is basically the same stuff which is defined in the model block. Here I'm just replicating according to the likelihood for future replications, but the likelihood for the likelihood for hypothetical replication, because these are in-sample replication, these are copies for my data, this is exactly the same likelihood that I'm using to fit the model. So basically what I'm doing here, for each values of my posterior distribution, I'm generating hypothetical replication for my data. Stan hides something in this case. Okay, this is a vector, let's say that this is a vector of dimension j, okay, and this is true. But basically, when you will be extracting Y-rep, this will be a matrix of dimension s times n, where s, capital S, is the number of iterations of your Hamiltonian Monte Carlo. So Stan somehow is hiding here for you, because Stan is very effective in this, in the vectorization. Stan is hiding that actually, yes, this is a vector, okay, but generally this will be extracting as a matrix S times n, with as many rows as iterations of the algorithm, as many columns as the dimension of the data vector. So will be a data matrix of dimension, let's say, I don't know, 2000, let's say, times 8, because I have just 8 data points. So basically, with this value here, I'm replicating hypothetical replication for my data process. So I'm, let's say, creating new copies for my data. Oh, basically, this is something that I already told you. Now we should visualize this distribution over the S draws and detect eventual deficiencies of the model. So now we should visualize what the generated quantities block generated. So we will perform many kinds of posterior predictive checks, but mainly we will be using visualizations. So all the plots are obtained with the bias plot package. As I told you, bias plot package is very effective also to give you some, let's say, model checking, some posterior predictive checking plots. So the basic idea of graphical model checking is to display the data alongside simulated data. So we can basically have a direct display of all the data. We can have a display of data summaries or parameter inferences, or we can also construct graphs of residuals or other measures of discrepancy between the model and the data. So basically we have many stuff. Let's go to see what happens. With the function, for instance, PPC dense overlay, as you can see, PPC dense overlay with arguments y, the data, observed data, and Y-rep. Basically, I'm plotting together the real data vector, so y, which is the dark blue line, along with all the data vector replications obtained from my model, the Y-rep. I will have as many Y-rep vector as, let's say, the number of iterations that I posed at the beginning. So let's see in this case that the blue line, which is the line of the observed data, lies within the cloud of the replication. So let's see that in this case, the blue line, which is the observed data curve, is somehow not distinguishable with respect to the simulated ones. So according to the data distribution, according to the approximated density of my data, we have not signals here to say that my model is not fitting well the data. Because of course, I mean, a problem would have been if my dark blue line would have been here, let's say, completely in another place with respect to the replicated data. But the clouds of the replicated vectors somehow contain the blue line, which is the curve for my observed data. So again, let's say that here the check is more graphical than, let's say, quantitative. We have to make a graphical check. We have to be, in some sense, we have to get used about the practical usefulness of these plots. This is, for instance, the same, but not for the density, but for the empirical cumulative distribution function. And basically, you can retrieve that, again, the blue line falls inside, within, let's say, the stream, the cloud of the replicated distribution. Then you can also, for instance, for each school, retrieve the posterior intervals, the predictive intervals for the replications. So basically, we will have the medians here and 50 intervals and 95 intervals. As you can see, the Y, also in this case, fall inside the predictive intervals. Some of them fall inside the 50 probability posterior uncertainty, the 50 percentage predictive intervals. Some of them fall within the 95, but all of them fall within the predictive interval. This is another signal that the model is likely to fit well my data, because here a possible sign of poor fitting would have been that the observed point were very, very far from my predictive intervals. And this is not happening in this case. So my Y data, my observed data, fall within, for each school, the predictive intervals obtained from data replications. Another kind of check is about statistics. You remember that I told you that we could, for instance, choose a scalar for checking whether my data replications are describing well my data. I can choose, for instance, the mean and the standard deviation. Again, the histogram is plotting the mean of all the replicated vectors, and the blue line is the mean of the observed vector. So here, how can you, in some sense, how can you interpret these histograms? Whenever your observed statistics falls within the histograms, you have signals to say, and you have signals to think that your model is fitting your data well. Some possible anomalies and some possible, let's say, dangerous signals are whenever your observed statistics falls in the tails of the replicated distribution for that scalar statistics. So for the mean, for the standard deviation, for the median, for the maximum. But all the scalar statistics here, all the observed scalar statistics fall within the cloud, fall within the histogram of the replicated scalar statistics. You can also, if you want, provide some bivariate statistics plots to see and to check which is the behavior of couples of statistics, for instance, the mean and the standard deviation, or also the maximum and the median. So just to have a very quick comment, the graphical summaries suggest that the model, in this case, generates predicted results which are similar to the observed data that we analyzed. And let's say that the observed statistics fall within the replicated distribution, and we saw this via check 4, but also the distribution of the data is coherent with the replicated ones, so check 1. Both the density and the empirical cumulative distribution function. Okay, so basically here we have good signals to say that this simple model for the coaching effects in the different school is, let's say, good enough to, let's say, explain my data. And how did I check this? By generating hypothetical replication from the posterior predictive distribution of my data. Okay. Do you have any doubt about this? Do you have any question, curiosity? Did you, is this clear? Okay, anyway, if you have some other, let's say, if you have any doubt, any, let's say, curiosity, please stop me and I can try to answer. Now, let's go through a practical case scenario. we will be analyzing the so-called cockroaches pest control example. So cockroaches data refer to a company that owns many residential buildings in the New York City. The company tells that they are concerned about the number of cockroaches complaints. I don't know how to how you call these beasts here. This in English, this is cockroach. So the company tells that they are concerned about the number of cockroach complaints that they receive from their 10 buildings. I spent 6 months in New York, and I can tell you that in the New York buildings, you can find rats, you can find cockroaches, you can find many other animals. So I'm aware of this. They provide you that you are the statistician. They provide you some data collecting in an entire year for each of the buildings, and ask you to build a model for predicting the number of complaints over the next months. So basically, the company is worried about the number of complaints about the cockroaches, and in some sense, for considering all the 10 buildings, the company is asking to to develop a model, a predictive model for the number of complaints over the next months. A good question then is, how should we analyze this data? So we have access to the following fields: the complaints, the number of complaints per building in the current month, and this will be our response variable. Traps, this is the number of traps used per month per building. Live-in super, this is an indicator for whether the building has a live-in super. Live-in super in United States is a person who is responsible for the house. So maybe I should expect that buildings with the live-in super are less likely to have cockroaches complaints. Then we have the age of the buildings, total square foot, so the total square footage of the building, the average tenant age, the monthly average rent for the building, the floors, which is the number of floors per building. So you should understand now that we have many covariates at the level of the buildings, and this will be relevant for our process, for our model developing. So now let me stop sharing the screen. If you want, you can follow the analysis now. You can open the RStudio console if you want. You are free to do it. You can open the R code folder, and you can open with me the pest control code 1. So let me now again share the screen for RStudio. Okay, you should visualize now my R console. Tell me whether eventually you cannot visualize the R Studio console. So I ask you to download and load some packages. These are very simple packages: RStan, dplyr, ggplot2, and biasplot. So basically, I've already launched this code. I want to show very quickly some stuff. So let's go initially to inspect our data. So we have basically 120 data points, because we have the number of complaints for each building followed per 12 months. So let's go directly on line 37. We load the data. Pest data is my data. Number of buildings is the number of buildings, and this is 10. And then we can have some very initially graphical plots. So basically, we can have the histogram for our data. And you should already have the idea that since we are working with discrete data, which are, let's say, quite asymmetrical, maybe a good solution could be use a Poisson distribution, a Poisson model, trying to model this kind of data. We can have different, let's say, initial ways to explore the data. So basically, we can have the number of complaints versus the number of traps, and color in different way the observation for buildings with the living super and buildings without the living super. We can have, for instance, in this case, let's see, in this case, we can have the historical time series for each building, so the number, in this case, of complaints for each building, and so on. But this is not something that I want to bother you. Let's go to directly access the data, and let's go to store in the list standard simple. This is the list for my Poisson model, because the first model that we are going to assume is a very simple Poisson model for the number of complaints. We are not going to consider any kind of structure. We are not going to consider any kind of hierarchical structure for the different buildings. We're not doing anything about this. We are just assuming that all the complaints come from, let's say, the same building. So very, very, very rough and stupid Poisson problem. So we are basically using a generalized linear model. So a Poisson model, and the only covariate that we are going to use, go back in the slide if you want to take again into consideration the covariates, is the number of traps. So the Stan model that we are going to use are saved in the Stan programs subfolder. So basically, you can open the simple Poisson regression.stan, because as you can see here, this is the first Stan model that we are going to use. As you can see here, basically, we have a function block. The function block, I have no time to inspect this quite deeply. But in the functions block, basically, you can define your own functions. So, for instance, in this functions block, it is defined a safer version of the Poisson distribution, which is well suited for numerical overflow. So if you want to define your own functions for your own distributional function or distribution that are not in Stan, you can define your own functions directly in the functions blocks. Then you can define your data, of course, so the sample sizes, which is n, the number of complaint, which is an integer. Pay attention, you cannot define this as a vector. You need to define this as an integer. This is your response variable, the number of complaints. You have to define as an integer because whenever you use a discrete distribution, like the Poisson or the negative binomial that we are going to see in a while, of course, your response variable needs to be defined as an integer. Then we have the number of traps. This can be defined as a vector instead, because this is a covariate, and we can define this as a vector, even if also the number of traps, of course, is an integer, because this is a counting covariate, counting how many traps has the building in that particular month. The parameters are only alpha and beta. Beta is the parameter associated to the number of traps, alpha is the intercept, and then here we have the possibility to specify some possible prior. Here I did just some very, very rough experiments, but for instance, I'm expecting that there is a negative correlation between the number of traps and the number of complaints. I can expect that in some sense, the higher is the number of traps and the lower is the number of complaints, because the more traps people are putting into the floors, and maybe the lower is the number of complaints. For the intercept of alpha, I use here a very illustrative normal distribution centered in log 4 and 1. So this is a normal distribution with the mean, which is of course positive, with the standard deviation of 1. You should immediately realize that the priors I'm using are quite weakly informative, as I said before. Why? Because I'm not using very diffuse priors with very high standard deviations, very, very diffuse. No, I'm using very strict priors. The standard deviation here is 1 for both the priors of beta and alpha. This because Stan and the Hamiltonian Monte Carlo, which is behind Stan, in some sense encourages the user to use some weakly informative priors and not to use very diffuse priors lost in the parameter space. The complaints are defined as Poisson log. Poisson log is the log likelihood of the Poisson distribution. And with the Poisson log, you can define directly your linear predictor here. So your eta usually. So Poisson log alpha plus beta times traps. So beta is the coefficient for the different traps. Of course, beta in this case is a real value. So is the parameter associated to the different traps. One of the nice issues of stan, as you can see here, is the stan, of course, allows for vectorization. So here you don't need to make a cycle for a small n from 1 to capital N, complaints n is a Poisson log. No, you can just write complaints. Of course, the dimension of complaints is n, Poisson log, and stan immediately realizes if everything is stored, let's say, in a wise way, in a right way. Stan understands that you are vectorizing your code. In the end, what you need, just do not focus for a while on line 38, because this is the pointwise log likelihood. This is for the end of the 2 hours. But on line 37, basically, we are producing hypothetical replication, which are again defined according to the Poisson distribution. Eta n is exactly the same linear predictor used to fit the model. So basically here I'm just reproducing something. This is a very simple Poisson model. A simple Poisson model in which basically I'm using some weakly informative priors. I'm using the Poisson log for the likelihood, for the log likelihood of the model. Remember that stan works in terms of log posteriors. And then I'm using the generated quantities to produce, let's say, S, capital S. I'm using capital S to indicate number of replication, capital S vector of replication of Y, each of dimension n. So I will be producing S replication of a vector of dimension 120. Okay, so basically I already launched the code for the simple Poisson. You can find the code here. I'm not going to describe the code quite, let's say, deeply because we do not have time. Let's go to see the estimate. So with the print, basically, you can retrieve the posterior estimation conclusion. And as you can see here, we find something that is familiar for us, because the posterior mean for beta is minus 0.19, so something like minus 0.20. So it is in some sense confirmed that there is a negative association between the number of traps and the number of complaints. You remember that when specifying the prior distribution, also we got something that was in the simple Poisson regression. The prior for beta was centered in minus 0.25. So I mean, this looks like cheating because the mean of the prior is also quite similar to the mean of the posterior. But just to, in some sense, give you the meaning of what is meant by choosing, in this case, a weakly informative prior. I could also have used a normal 0-1, and it is quite likely that the posterior results will not change so much, because of course the data are very informative. In this case, I have no reasons exactly to give this kind of a mean. But in the mean of the prior, I can in some sense translate the idea that I can expect from my data, from my posterior, estimates for beta, that beta is negative, because I can expect a negative association between the number of traps and the number of complaints. Okay, let's say that in this case, I could, for instance, again produce some very, very simple, let's go to line 90. So I can produce the histogram, for instance, for beta and alpha, so the marginal posterior. And then, and this is what is basically very important, I could extract the hypothetical replication from my data. I could do this in many ways. I use this, the command s.metrics, name of the model fitting. The parse that I want to extract is called yrep. So line 94, let's launch line 24. And now we can, with the PPC dense overlay, we can directly depict the posterior predictive distribution for my hypothetical replication against the distribution for my data. Sorry. Immediately we notice something. We notice immediately that in this case, the cloud of hypothetical replication is not mirroring perfectly the curve, in this case, of observed data. As you can see here, the model is also underestimating the number of zeros. As you can see here, the tail of the distribution here in 0 is not effective. So there is a sort of lag in the model replications. So maybe even from this first plot, I could have the signal that the model is not much suited to capture, in some sense, the pattern of the data in a very satisfactory way, because it is underestimating the number of zeros, as you can see. It is not capturing, let's say, the pattern of the observed data. And so maybe I could also go to see directly, for instance, if I compute the proportion of zeros for all the replicated vectors, so I create the function prop0, I could see, for instance, that by creating the histograms, as you can see, the blue line is the proportion of zeros in the observed data vector, whereas the proportion of zero distributions in the replicated vectors is completely far from the observed one. So basically, I'm going to have some signals that the model is not suited enough to describe, for instance, the proportion of zeros. Let's go then to see, and then we take a break, but let's go also to see what happens in terms of the standardized residuals. So I can construct the standardized residuals directly from my hypothetical replications. And what we see, okay, the standardized residuals should be, if the model is fitting well the data, should be bounded between approximately -2 and 2. I have here many standardized residuals exceeding the bands 2 in this case. So maybe the model is not capturing well the so-called over-dispersion nature of my data, because we already had a glimpse about this. We had already the glimpse that the model is not able to capture the proportion of 0. Maybe there is a problem with the over-dispersion of my data. And we already know that the Poisson distribution is not suited to capture over-dispersion. Remember that in the Poisson distribution, of course, the variance is equal to the mean of the process. Let's go again to see what happens in terms of predictive intervals for my model, for all the 120 for the 120 building. And as you can see here, let's say for some of them, the observed values fall outside the predictive intervals. So in some sense, we are having some, let's say, possible, signals that the model is not able to capture very, very well the nature of my data. Okay, so maybe we have to go beyond. Of course, we can have multiple extension. So we could consider an offset, for instance, an offset which takes care of the different square foot of the different buildings. Because whenever in a Poisson distribution we have different exposures, it is, let's say, suggested to use the offset trying to capture the different exposure. And the exposure in this case, for instance, is the square foot of the different buildings, because the bigger is the building and the more likely is to observe complaints, maybe. So we have to put in a more homogeneous way the observations for the different complaints. So we can fit a model with the offset. This is called the multiple Poisson regression.stan. It is quite similar to the previous one. We can extract also from this model, once you launch the hypothetical replication, and then you can try to check this model again with the same, exactly the same tools that we used so far. So in this case, with the PPC dense overlay at the beginning. But you immediately realize, yes, the model slightly improved, slightly, but not so much. So maybe, yes, it's better than before, but still it's not perfect. Let's see what happens with the proportion of 0 statistics. computed over the over the S replications. Let's see what happens. And we realize that, okay, maybe the histograms is closer to the observed value for the statistics, but still it's not, let's say, satisfactory. Let's see see what happens for the posterior predictive intervals. And again, we find that some of them, a proportion of them, is exceeding, let's say, the predictive intervals produced by the model. So maybe it is time to go through, let's say, another kind of model, a model which is, let's say, more slightly more sophisticated. Let me go back to the slides, and then we take a 5-7 minutes break. So we are in the slides. I already covered this with our example. So the Poisson distribution. So let's go directly to the slide number 64. So in some sense, we can check that the Poisson distribution maybe is not suited enough to capture the nature of my data. That's the reason why now we have many possibilities. What to do if a posterior predictive check in a STAN model fails? So there is not a unique answer, of course. However, we can do many stuff. We can extend the model by putting more covariates. I've already put the offset, and the situation is not improved so much. But I could include eventual hierarchies. I could change the sampling distribution. I could change the prior. I could transform my data. So basically, in what follow, we do not include further predictors beyond those that I explained so far, but we will work on both the choice of the sampling distribution, so not Poisson anymore, and finally, we will also be considering some hierarchies. Because remember, data, in this case, are clustered within buildings. They are not coming from the same building. So maybe we could use this to develop more sophisticated models. So the first step, and then we take a break and then we see these steps, is, for instance, changing the sampling distribution, not anymore a Poisson distribution, but a negative binomial. Okay, guys, any question, doubt, comment? Let's take a break. See you here at 5:45. So see you here in 8 minutes. We go ahead with negative binomial example, hierarchical model, and then also we will be finishing by also comparing models. I will be giving you some guidelines on how to compare model with the predictive information criteria, which can be used in STAN. Okay. See you in 7-8 minutes.